working on tests about a population proportion, and those involved Z distributions because proportions are based on the entire population. So that's why that would use a Z. But when we're doing inference about a population mean mu, since we don't know everybody out there, that's why we're taking a sample. We're taking a sample to predict about the population. But since we don't know everyone, we know that we have to use the more conservative T distribution that's going to be a little wider than the Z distribution. So we're going to use that, except for in the very rare case where you have known standard deviation. How would you know if you had the standard deviation known? In the AP test, it happens very seldom, but probably in the multiple choice is most likely. But how would you know it? They would have said that you had a standard deviation from a past study. So they say, last year the standard deviation was this, and now you're doing a new study with this old standard deviation that you had from the past. Or they would explicitly tell you by using the sigma symbol, and that would tell you that it's a known standard deviation because they stated it with the actual symbol. So if you, whether you have known standard deviation, whether you have a sample statistic for the standard deviation, your test statistic right here looks like this. You're taking your statistic minus your parameter, and then you're dividing by the standard deviation of the statistic, which is right here, the sigma divided by the square root of n. That's your standard deviation of your statistic. But when it's T, that really works the same way. However, it's actually referred to as the standard error because it involved a sample statistic in its calculation of the statistic. So this will be, so using T's, you're going to be using standard error in the denominator right there. So before we can do any inference, before we can use any of our calculator commands that are similar to the ones for the normal curve, but now involve the T distribution, we still need to meet our conditions, and especially the normal condition, in order to use these curves. So let's examine a situation for AAA batteries and see if this meets the conditions for inference. Okay, a company claims that they have a new AAA battery and it's going to last longer than its regular AAA batteries. From the past, they know that it was lasting 30 hours of continuous use. But they just went out and took a sample of 15 new batteries, and they see that it's lasting 33.9 hours with a standard deviation of 9.8 hours. So first thing I'm going to do is just look at what they gave me for information in the problem, and they gave me statistics of 33.9. Oh, let me write hours on there. Gotta be good about my units. And 9.8 hours for the standard deviation. So that helps me decide what I'm going to think of as being my mu, my population value that I'm testing against for my hypothesis. If I meet the conditions for inference, then I would do that. So looking at my conditions, first of all, is this random? Is this? Yes, it was given. They did an SRS. So that is meeting that condition for inference right there. Is it independent? You have a finite number of batteries out there in the world. So that's going to mean that we will need to use our 10% condition, making sure we don't exceed 10% of the population in our sample size. And 15, I would say, it is, if N is 150 batteries or more, then then okay. So like that seems reasonable to think that this company that's making money making batteries is probably making at least 150 batteries. Now the nearly normal condition. Now with T distributions, they are robust for T. And so think about the ways that you would check to see if something was meeting nearly normalcy. So if it was already stated to be normal, that would meet the condition. If it was over 30, that would meet the condition because you would have CLT. If you were between 15 to 30, you can have some slight problems about normalcy, like there can be some skew, but definitely no outliers. We're at 15. If you're below 15, you'd need to have no clear skew, no clear violations at all. But we're at the 15, at n equal 15. So we can have, slight skew is okay, but we don't have any information about that. We can have no outliers, but we don't have any information about that. We would need to know that. So right now, we cannot establish normalcy, but we do know T is robust. So we'd need more information, and it's a good thing that on the next page we have it. So let's go to the next page. We would need to see this data, or at least get some other information, info to help us decide about this. So we are going to put this data in the calculator, and here is my histogram. Actually, this is not a histogram. I would use a histogram, but this is not a histogram. This is a dot plot. But on the calculator, we could just use a histogram. This is to check for our outliers. And we can look at that to see if there's any outliers. And this is our normal probability plot. Last option on the stat plot options. And we want this plot to be straight or approximately straight. Let me put approximately on there. We want it to be approximately straight. Don't get confused. This is not a residual plot, which was for linear regression. So don't get confused and think like, oh, remember there's our model for linear regression, our y equals a plus bx. Like there's our model for that, and we wanted to have that chance scatter where our model was over predicting and under predicting, but in a seemingly chance way where there wasn't something systematic going on there. But so that's not what we're doing. We're doing a normal probability plot. We want it to be straight, and that's the most helpful graph to see if we are looking like normal. So I would say from the dot plot, it's hard to really tell the shape of this. You could almost say it looks uniform, but like you have no clear skew going on. So like no skew really evident. That's good. That's meeting that. From our box plot, we can see that there are no outliers. That's very important at that 15, n equal 15 level. And then our normal probability plot is approximately straight, and that's our most valuable tool to see that I would say we are meeting the nearly normal condition for this. So we are going to complete the conditions for inference are met. Met, and it says there, if appropriate, complete this test. We are going to do a one sample t-test. We don't know we have sample statistic for standard deviation. We don't have a known standard deviation, so we're going to have to do a t-test for means. Calculator refers to it as a t-test if you're going to use a calculator to check yourself. So doing a one sample t-test for means. Okay, conditions are met. Let's write our hypotheses. Notice how I'm using the population symbol for my null hypothesis. I'm using the population value that we used to have these batteries, and we want to know if they're going to last. Well, do we want them less than, not equal to, or greater than? We want them to last longer than 30. We're looking at this situation right here. If our old batteries were at 30, we don't know if our new batteries last longer, but right now we're only interested in changing our production if we see the batteries are lasting longer. And right now we saw a value of 33.9, but we don't know if that's going to be significant at the alpha equals, let's see, what level did they say in the problem? They didn't give us a level to do this test at, so I'm going to then use my favorite value, the 0.05 level. And I do not have known standard deviation, so I'm going to do my standard error, which on your formula sheet you can see that they have this symbol. I also like to use this. Sometimes I use SE for standard error, but both of those are, notice the line on top, that's making it different from when I write it like this, there's no line on top, but so I need my standard deviation, 9.8 divided by square root of 15, I get 2.530349112. I have to, because I'm doing a t-test, I need my degrees of 15. Remember, degrees of freedom is n minus 1, so 15 minus 1. I've got 14 degrees of freedom. That is on the table. That is in your AP formula sheet packet. Okay, let's continue on. We're going to find the t-value. Statistic minus parameter. That middle, there's my parameter right there. And then let's put the standard error underneath that so we can find our test statistic, which is very, very important too. For the t, you have to have the test statistic in order to put it into the calculator. You'll need that. And so then we're going to find, here's my notation, I'm going to find the probability that my t is going to go above a 1.5413. And the probability of that happening, now you wouldn't write this on your AP test, but I'm basically going to be doing TCDF. I need, here's my left, some really big value for my right. So 1.5413, really big value for my right. That's huge. 10 would have been big enough. And then the degrees of freedom go right here. So that tells the calculator how to fit that curve. So let's see, let's put the value for this. Oh, now 0.07277. Of course, I wrote that DF right where I wanted to write my probability, but anyway. Okay, since the p-value, because that's what this right here is, that's my p-value. Since the p-value of 0.07277 is, let's see, is it less than, greater than? It is greater than alpha equal 0.05. We fail to reject the null hypothesis. Hypothesis, and there is not significant evidence that, like, come back in like half an hour, that there is a different, that, or that the batteries last longer. We got to word it in terms of the alternative hypothesis that the batteries last longer than 30 hours. So, I mean, even though those batteries seem to have lasted longer, it's not statistically significant that they're lasting longer. So I would not, don't change the production for these batteries. They don't really seem to be doing what they were promising. And then we can verify our results using our calculator under stat tests, the t-test option, and you can put in data, or you can put in the summary stats, in our case, summary statistics, and it would verify that we get the exact same value. We'll do a test with that on later in the, do it in the calculator later in the unit. Okay, so we're going to use a test, a t-test, only when the population distribution can be shown to be normal. And we know that for the t distribution, it is robust, so we can prove this normalcy is happening even at lower levels than 30, because if it's over 30, we're meeting CLT. But if we're lower, we're going to have to really dig into it to see if we can prove it. And then right here, 10 times as large as a sample, that's proving our independence. That that's going to help us be able to do this standard error right here. Independence is about making calculations on that. So here are the different setups that you might have for your one sample t-test. You could be testing a greater than, you could be testing a less than, and you can see the way that that would be shaded. And then here is the two-tailed, where you're going to have to double. This is a statement of difference. If there's a difference, a not equal to situation. So we'll watch for that. And that's the kind of situation that is related to confidence intervals. And so let's look at the two-sided test for a population mean. Okay, so first of all, let's read this information and see if we have known standard deviation, or do we have a sample statistic for our sample standard deviation. So let's see which one we've got. We have these pineapples. The mean weight from this field was 31 ounces. Is that going to be my mu, or is that going to be my X bar? Well, let's think some more. Let's read some more. We have a new irrigation system in this field. Managers wonder if this change will affect the mean weight of future pineapples grown. To find out, they select and weigh a random sample of 50. So 50 pineapples from the crop, and then this Minitab output summarizes this information down below. And here's what our sample resulted in for our pineapple weight. This standard deviation right here is not a known standard deviation. It's based on a sample, so that is an indication that we would be doing a t. But right now we're just checking our conditions to see if this is even something that we can do. So we needed to know about the shape. Whoops, shape. Let me erase that and spell shape correctly. All right, we need to know about the shape, but do we, with n are nearly normal, it meets CLT. But I still want to check. They've given me the information. I can still check for outliers. If we had outliers, we would want to run the test twice, once with the outlier, once without the outlier, and compare the results. And hopefully those results would be pretty much the same. When they aren't the same, that's when we have to think about what it means and what is more correct for our situation. Use some judgment. Okay, so first of all, we need our IQR. That's based on our Q1 and Q3, because Q3 minus Q1. So we get 34.115 minus 0.990. I get an IQR of 4.125. Now, if I want my max typical above this value, then I will call you an outlier. That's my Q3 plus 1.5. Okay, so we're going to take my Q3. Okay, let's see here. 50, there's a sigh. 40.2985. And then on my min typical, that's going to be Q1 minus 1.5 IQR. And so my min typical, it was, let's see, 29.990 minus 1.5 times 4.125. And I get for min typical 23.8025. So now, okay, that I got to look. Here's my, right here, my max at 40.2985 and my min at 23.8025. These are the typical, but then like where did my max and my min fall? So like maybe my true max here at 35.547. My true min somewhere, I don't know where it is on this number line. I'm not really drawing to scale, but 26.491. There's that min. So they are within. That would mean there are no outliers in our situation. That's good, because that I would say our conditions, well, we should actually check our randomness. Random. It was given an SRS of pineapples, so that meets that. Independent. They're making money making pineapples, growing pineapples. Finite number of pineapples out there. 10% condition is required for this. I would say that there are more than 500 pineapples in the field. I mean, how are they a business? And making good money if we would hope they have more than 500 pineapples. So that to me says that the conditions for inference were met. And therefore, I would say we're going to do a one sample t-test for means. Yeah, we're not getting out of doing this problem that easily. On to the next page and let's do it. So here's our same pineapple Minitab output. And now we're going to do it because the conditions are done. That's done. We know that we're doing a one sample t-test for means. We know mu is going to be our the weight of mean weight of the mean weight of a pineapple, and that would be in ounces. Okay, condition. Got the conditions. Hypotheses. The former pineapples were at 31 ounces. And so we are seeing if our pineapples, our alternative, is it going above 31 ounces? We only care about that. Or is that what they said actually? No, they said in the problem that they wanted it to be different. They wanted my pineapples to just be different from the past. That's actually a two-tailed case where if you have 31 in the middle, and this is, we got this 33.9, but they didn't say like they only want this side. They said, we want you to be different. So I have to change this. Well, I'm really, that's from the batteries. 31 ounces. Okay. All right, so we have our significance level of 0.05 since they, I don't know if they gave us didn't see a significance level. So let's call it the 0.05 level. And my degrees of freedom will be n minus 1. So 50 minus 1 is 49, which isn't on the formula sheet. So if you were going to use that, that table on the AP sheet, that you have a choice. Are you going to use 40? Are you going to use 50? Well, let's remember, we always like to be more conservative. So you would use a 40 because it's going to be a wider interval for the t distribution. So that would be what you would use. And so now let's get my standard deviation for the sample statistic. I mean, standard error of the sample statistic. 2 point. Which it's funny, if you look at the Minitab, see if you can find that number in the Minitab output. Oh, they gave you the standard error right there. So we actually had that number already. Let's see. Let's now do our T, our test statistic. And I get for that 935 over 0.335. And so around 2.758. My notation for what I'm the probability I'm trying to find. What's the probability that my T will go above a 2.758? And using my TCDF, I get a probability of 0.004074. But because it was two-tailed, I've got to double. I've got to double this because there's that other area down here that is the exact same size, and so I've got to double it. And so there we go. Since that's less than 0.05, so since the p-value of, make sure you're always stating your numbers, is less what you're finding about them, alpha equal 0.05. That, so I've got both those numbers. What am I comparing? What am I comparing it to? We reject. There's my decision. The null hypothesis. And there is significant evidence that, and then make sure you're the context of what are we testing. We're looking at this alternative hypothesis. It's got to be worded in that there is a difference and the pineapple weights have changed. they are different from 31 ounces. And I mean, I'm not an English teacher, so maybe you can make that sentence sound a little better. Okay, so that was the test. And so we're thinking, okay, we've done something, it's made a change, and our pineapples are now different from what they were before. That could be interesting for us to do if we want to change our production. Okay, now we're doing this test of mu. Sometimes in your output, they're going to, they might not have this Greek letter mu, and so then they might write it something like this. You need to say, well, this is a test of mu being 31 versus not being 31. So that's what we had written on our alternative hypothesis. And this is some output that tells us a little bit more information. It still has the n and the mean and the standard deviation, and it has our standard error of the mean. But this one's giving us a confidence interval as well as the t-test statistic and the probability. Output like this is always two-tailed because it's related to the confidence interval. Confidence intervals are two-tailed, so they have, a higher and a lower. So if you wanted a one-tailed, if you want one-tailed, you would have to cut it in half. So let's write that down. One tail only, you have to divide by 2. So like make sure that you're aware of what kind of test you're doing. But this one, I'm looking at this confidence interval and they gave it to me. There's with the parentheses and the comma really just saying this right here. And notice how I'm using a parameter in the middle there, a parameter symbol to show that this is my best estimate. Every time I go out and take a sample, I'll get a new estimate, but this was that particular estimate based on this particular mean. I got that estimate, and this 95% confidence interval for the mean weight of all pineapples grown in the field is 31.255 to 32.616 ounces. And then we're 95% confident that this interval captures the true mean weight mu of this year's pineapple crop. We know that it either caught it or it didn't. The true mean is a fixed number, and every time we go out there, we know that the true mean stays the same, but our confidence interval will change, and maybe sometimes we caught it, maybe some other times we didn't. But there's a very good relationship between the confidence interval and the test. As with proportions, there's a link between this two-sided test at a significance level alpha and our confidence interval based on that same alpha, on that confidence level for the population. And this link is even closer when we have using t's because of the conservativeness of it. But so our pineapples, we had two-sided test at the 0.05 level. Remember, we rejected it. We rejected the null in favor of the alternative hypothesis. And if you look at our confidence interval of 31.255, think about, is 31 in that interval? No. So because 31 ounces is not in the interval of, remember, you always have to say the numbers, 31.255 to 32.616 ounces. It is reasonable to conclude that pineapple weights have changed. from that previous value of 31. And you're going to see a relationship between the tests and the confidence intervals that they're going to match up. And on the next page, it basically says that if you have your test statistic T, you've got your confidence interval based on a critical T value that varies along with your degrees of freedom. The two-sided test at a significance level alpha is going to give similar information between your test and your confidence interval. They are going to give similar information. And so when your two-sided significance test rejects, then mu will not be within our confidence interval. When we fail to reject, remember, we don't accept things, we fail to reject it, then we expect that the mu will be contained within that confidence interval. So that's that. Now let's do one more example of a t-test for means, and this one being a matched pairs design. So if we're doing a comparative study and we're doing a matched pairs, a well-designed experiment where we have randomization of the order of the treatment. In this case down here, we have someone who's they're trying to find out if caffeine deprivation, if you're getting deprived of your caffeine, is that going to increase, not just change, increase your depression. So let's look at what they said here about these measurements. They're studying this caffeine. They've recruited 11 volunteers. They were barred from any coffee, colas, and other substance with caffeine during that period. They're going to take these capsules containing their normal, their individual normal caffeine. That's control right there. And then during the other 2-day period, they're going to take the placebo. And the order in which they do this is going to be randomized. And so that's good for our randomization. And so here's the results for subject 1. They had a 5 for depression with caffeine, a 16 for depression without, so their placebo minus caffeine is 11. So I'd say that looks like more depression for that individual. Now, when you're doing this, you don't want to be thinking of it as the mean. You don't want it to be caffeine minus placebo. You don't want to be taking the mean of the caffeine minus the mean of the placebo, because that would be all this variation for taking caffeine depression, all this variation for placebo depression, and then you would have all this variation that you wouldn't be able to distinguish between the individuals. That would be the wrong way to look at this information. Instead, you want to be taking the mu, you want it to be the difference. So like for each individual, you need to find their value of placebo minus caffeine, and we need to find out what that is. So let's go to a calculator. And here's my calculator. I put the caffeine levels and the placebo levels in there, and I'm going to now just show you really quickly up here on the L3. I'm just going to say, let's take my L1 or L2, because we said we're going to do placebo minus, just in case you had to do this yourself. There you go. You've got your numbers. And if I needed my statistics, I would do my statistics just on the just on that L1 list. This is the old software, so that's why I have to enter it in that way. But there's my old list with my 11 people. I can look at that. But before I can do that, I need to look at my conditions for inference, and I had raw data. So with raw data, I'm going to have to look at my my normal probability plot, my histogram. So let's go in there and look at a histogram of this data. Let's see if that's, there we go. And you can see the histogram on the screen there. If I wanted to change the window, I could change my spacing. Maybe I want to change my scale to something a little bigger just to see what that would do. Why don't I just change that to 2 just to see what it does. Let's see that. Yeah, you know, it doesn't look like there's skew. Just kind of, there's not a lot of data. There's only 11 values. I don't see any clear violations. It's kind of hard to really get a feel for the shape, but no clear violations. But better to look at the box plot anyway. So let's look at the box plot, see if there's any outliers. Let's do it and hit enter. Let's go. Oh, okay. So looking on my screen here, I'll make it bigger. There, no outliers, which is a good sign because at 11 you absolutely can't have any outliers. And then my last graph being my normal probability plot. Let's go in and look at that. Whoops. These are good times. All right. There's my normal probability plot. And look at that bad boy. And that's maybe a little wallop in here, but like it's reasonably straight. That's straight. Now, you just went and did all that work. So make sure that you show it on your AP test, that you checked your conditions. Are we random? It was an SRS. It was a matched pairs design. Okay, are we independent? We have people. So with 11 people, I think this is trying to make a prediction about people out there in the world. There are more than 101 caffeine drinkers. Have to be there. And then, okay, nearly normal. So our N is less than 15, but T is robust. We've established normalcy by looking at the graphs. So show those graphs that you checked and make sure you give it a rough scale on what the graph. I can't see what the graph shows, but like with something like this, you know, I'm not totally sure about that number, but you know, make sure you put some numbers on there so that somebody can tell what that rough graph was of. And then my box plot, again, some rough numbers just so that they know that you like really looked at this. Whoops, let me start that again. It's not. My box plot was something like this. I can't see it because I'm in the other window, but you have it on your screen, maybe, hopefully. You know, something like that, you know, but, you know, identify that there were no outliers. Oh, and let me say no obvious skew. So that's good. And then, of course, our most important and favorite thing being, you know, again, with the numbers, you know, have some numbers on there. What numbers they were, I don't even know what the number was. But you would have it using your trace feature. You could get that. So the conditions are met. Let's do a 1 sample t-test for means, and it's for the difference of the caffeine values for our paired data. Okay, so our null and alternative, we have the difference here. Now, if there was no difference between the two things, then my placebo minus my caffeine should be exactly the same. Oh, that means that I should be equal to 0. And they are wondering if there is a difference. Are they wondering for a difference, or are they wondering if it'll make you more depressed, less depressed? Let's see here. Looking back, they want to know if it will lead to an increase of depression. So let's say I'll erase that. I'll make my son happy. Fix that. Okay, my greater than 0. And they said, well, let's do it at the 0.05 level with degrees of freedom of 11 minus 1 equals 10. Make sure you tell me what degrees of freedom, very important. Here's my curve, 0 being the middle, and I went out there, and if you recall from when I did the stat window, we calculated a mean of 7.3636. And we calculated, using our 1var stats, a standard deviation of 6.917698. So those are going to be our numbers that we're going to be looking at this. We're wondering if there's our area that we're looking for, one-tailed test, because we're just looking for greater than t equals 7.3636. Bring that 0 down from our null hypothesis, 6.917698 square root 11. There's my standard error, and that t-value comes out to be 3.5304. Well, I think there's looking like there's some kind of a difference here, but let's continue and find that probability of a t going above a 3.5304. We get, let's see here. I got to plug that into my calculator and see what that is. Okay, TCDF. Okay, for that value, and 100, and you could get this off your formula sheet because it is pretty low. 27215. Well, 9. But then I don't double it. No, don't double it, because we are only doing a one-tailed here for the being greater than. So since the p-value of 0.002721, well, let's 6, I guess, is less than alpha equal 0.05, we reject the null hypothesis and there is significant evidence that no caffeine, I think I spelled that wrong, but anyway, no caffeine increases depression. Well, it's a good thing I had some coffee this morning. Now, using your tests wisely. Significant tests are used in many research fields. I mean, we have to know, is there evidence that a new drug is effective and safe? So, you know, we use these in all kinds of situations in court and all kinds, because like, how do you actually know that something is really changing, or really the result like appears to be not just chance variation that's out there in the world, but actually creating some kind of an effect? Our null hypotheses are always our statements of no effect or no difference, and we're looking for the evidence to reject that claim. But we have to be aware that sometimes it's hard to detect a very small difference. So a very small difference can be highly significant when a test is based on a large sample. So we always have to like look at that and see if it actually really makes sense. A lack of significance doesn't mean that your HO is true. Sometimes you just, when you have a small sample, it's hard to detect these statistical differences. And significance tests are not always valid because, like, if you have violations of your conditions or other kinds of situations, then you need to be always thinking, you know, about the real life situation and how it really is true or makes sense. So always using your common sense when you're looking at your statistical studies. Now, if I can just figure out how to end this thing.